Despite existing on a small planet in a tiny corner of the cosmos, astronomers know exactly how much visible matter the entire universe should contain. The problem is that for decades, 40% of it has been missing. And I'm not just talking about the ever mysterious dark matter and dark energy. Galaxy clusters don't seem to have as much visible mass as our models say should be there. Entire galaxies seem to have lost huge reservoirs of the material they were born with. Even the space between galaxies, enormous cosmic deserts, are emptier than our best theories predict. This missing mass has to be out there. That, or all our models of cosmology, are wrong. But every time we've looked, we've found nothing. And believe me, we've tried. We've used our most powerful telescopes, deepest surveys, and most sensitive detectors in the search. The missing mass just remains invisible, slipping past our instruments like a ghost. That is, until now. For the first time in history, we may have finally found where the missing mass of all the universe has been hiding, and it's in plain sight. Astronomers have captured images of vast gaseous filaments that stretch 23 million light years between galaxy clusters. It may just be one filament, but finding it has huge ramifications. Is this the very first detailed image of the cosmic web? As scientists now hunt for more, this discovery has the power to determine whether our cosmological models are correct. I'm Alex McColgan, and you're watching Astrum. Join me as we reveal how astronomers have snatched a glimpse of the near-invisible network that underpins the cosmos, finally revealing the hiding place for our universe's missing visible matter. And with it, let's start unraveling the truth behind our cosmic evolution. When we measure all of the gas, dust, planets, stars, and galaxies, everything we can see in the whole universe, using everything from infrared to visible light and beyond to gamma rays, it adds up to a colossal amount. More than 100 sextillion kilograms. That's 10 with 53 zeros after it. But really, this only accounts for a small fraction of the total matter that scientists predict to exist. In fact, this visible ordinary matter is thought to make up just 5% of the universe. The rest is stuff we don't completely understand. Dark matter is believed to account for 27%, and dark energy 68%. Despite their names, dark energy isn't related to dark matter. What they have in common is that we can't detect or see them. Dark energy is thought to be a seemingly invisible type of energy, causing the universe's expansion to accelerate over time. And dark matter is a type of matter that has mass, but is invisible to us, as it doesn't absorb, reflect, or emit any light. I've talked about dark energy in previous videos, and that is truly its own mystery. You can explore those if you're interested to find out more about the topic. But for this video, I'll just focus on the matter at hand. So, 95% of our universe is likely not made of visible, ordinary matter. And of the 5% that is technically visible matter, also known as baryonic matter, about 40% has been missing since the Big Bang 13.8 billion years ago. Now, I know what you're thinking. How do we know it's missing if we've never seen it? We certainly weren't around back then. Thankfully, the early universe itself left us the answer. Measurements of the cosmic microwave background have allowed cosmologists to calculate exactly how much baryonic and non-baryonic matter was created as a result of the Big Bang, to an accuracy level of better than a few percent. That gives us a precise budget for how many atoms should be in the universe today. But just because it's made of stuff that's visible to us doesn't mean it's easy to see. When astronomers go out and count up all the stars, gas, dust, and plasma we can see, with the help of models and simulations, we only find about 60% of what should be there. The rest has to exist for early universe physics to make sense, but unless we can find it, we can't prove that our models are right. Maybe we've got it all wrong. Thankfully, scientists haven't been that quick to give up, and instead turn their attention to working out where the missing mass may be lurking. And they came up with an intriguing hypothesis. Missing baryonic matter is not the only missing mass, and perhaps they're hiding together. Nearly a century ago, Swiss-born astronomer Fritz Zwicky noticed that galaxies in the Coma cluster move too quickly for the amount of gravity that would be created by their visible matter alone, yes, including the missing stuff. Instead, he thought another form of mass must be there, and in 1933, Zwicky dubbed this missing substance Dunkle Materie, the German for dark matter. In the 1970s, American astronomer Vera Rubin had a similar experience. She was observing spiral galaxies and wondered how stars on the outer edge of the spiral galaxies were able to move so quickly without flying off into space. Again, some unknown mass must have been pulling them back in, and she concluded the same as Zwicky. There must be dark matter holding them together. This new type of stuff interacts with its ordinary baryonic counterpart through gravity, but it doesn't interact with the electromagnetic spectrum, meaning that it doesn't absorb, reflect, or emit any light. This makes dark matter extremely difficult to find, and seemingly impossible to observe, at least directly. Yet it influences the cosmos on a galactic scale. It may even be helping to conceal our missing baryonic matter. Since the 1980s, early observations of galaxy distribution have revealed a cosmic pattern, a web, like a backbone across the universe. This skeleton-like structure has become known as the cosmic web. It's thought to have formed as a result of slight density fluctuations in the early universe, which can be seen in the cosmic microwave background, or CMB, a fingerprint of our universe's ancient microwave radiation from about 380,000 years after the Big Bang. These tiny fluctuations in density laid out a blueprint for where matter would collect over space and time. Where there were higher densities, more mass would be drawn in, until this great structure was formed. We already know that CMB simulations using supercomputers estimate that dark matter accounts for 5 times more of the universe than ordinary matter, so it's perhaps no surprise that the cosmic web is thought to contain primarily dark matter. Permeating every corner of our universe, it's made of filaments stretching tens to hundreds of millions of light years across the universe. Where filaments intersect, the concentration of mass is so great that high-density nodes are able to form, containing hundreds or even thousands of galaxies. The cosmic web is real. We've mapped large swaths of it. Our galaxy is part of what's known as the local group, a collection of a few dozen neighboring galaxies near to our own. Our local group belongs to a larger collection called the Laniakea supercluster, which contains some 100,000 galaxies and measures 500 million light-years across. As you might have guessed, all these galaxies are strung along the cosmic web like beads on strings, perched along the edge of great voids. But even though we've been mapping this cosmic web for decades, most of what we can see is the beads, the distribution of galaxy clusters along the web, not the strings that hold them together or the filaments themselves. Or is it? Whilst most of the visible matter in the universe is tied up in galaxies, not all of it is. The dark matter in the cosmic web has a pretty strong pull itself. There, bound up as vast diffuse gas in those long strings or filaments, is where large-scale cosmological simulations have predicted we might not only find dark matter, but our missing visible matter too. This low-density, diffuse gas is known as the warm-hot intergalactic medium. But simulations are one thing, detecting these diffuse filaments is another. And this is where historically we've not had much luck, although that started to change about 20 years ago. In 2005, NASA's Chandra X-ray Observatory imaged two huge intergalactic clouds of diffuse gas. We'd seen clouds like this around our own galaxy and in others local to us, but not between distant galaxies. Could it be gas on the cosmic web? This was some of the first evidence that the cosmic web was hiding our missing mass, but the light was too faint to completely isolate it, so scientists couldn't quite be sure. Then, in 2012, a combination of 18 Hubble images was used to infer the presence of a filament funneling matter into the galaxy cluster MAX J0717. Scientists found it by studying the distortion of light from background galaxies due to the gravity of the filament's dark matter. But again, it wasn't a direct detection. We still couldn't say we've actually seen them. Inching ever closer to a discovery, it was just 2 years later that astronomers moved beyond indirect detection and statistical evidence into the realm of the visible. A team led by Sebastiano Cantalupo from the University of California observed an enormous filament of hydrogen gas. At nearly 2 million light-years across, they spotted it after it was illuminated by a giant cosmic flashlight, a bright quasar shining at it from 10 billion light-years away. This was the first time part of the cosmic web had been seen directly. Using the same illumination principle, in 2019, astronomers revealed whole networks of hydrogen filaments surrounding a massive protocluster, directly imaging the web on megaparsec scales. But these detections were only possible thanks to our cosmic flashlights. To understand cosmic filaments as they typically exist, in darkness, we needed a new imaging technique. And in 2023, scientists made a breakthrough. At the W.M. Keck Observatory in Hawaii, a team of astronomers had designed a dedicated instrument to search for filaments of hydrogen, more specifically, dim Lyman alpha emission, the spectral fingerprint of hydrogen as it absorbs and re-emits radiation. And it worked. In fact, they've made entire 3D maps of these filaments. This was just the start of the discoveries. In January 2025, the picture sharpened dramatically. A team of international astronomers captured one of the clearest direct images yet. Using the Multi-Unit Spectroscopic Explorer, or MUSE, mounted on the Very Large Telescope at the European Southern Observatory, they imaged a pair of quasar host galaxies with a cosmic filament about 3 million light-years long. And using supercomputer models built on the MUSE data, researchers were able to simulate a filament that matches the one they observed in real life. This was a spectacular achievement. But there was a catch. These observations were from the early universe. They traced cooler hydrogen gas billions of years in the past, not hot, diffuse material thought to contain most of the universe's missing baryonic matter today. Our models predict it stretched along thin filaments of the cosmic web in the local universe, but here the signal is far fainter and harder to isolate. We were stuck. In June 2025, astronomers finally found what they were looking for. They were able to isolate and spectroscopically measure the hot, low-density gas of an individual cosmic web filament in the local universe, marking a breakthrough moment in our quest to locate the missing baryonic matter. A team of European researchers headed by lead author Konstantinos Migas at Leiden University in the Netherlands used JAXA's Suzaku X-ray Space Telescope to map a single filament in faint X-ray emissions over a wide area of space. They then used the XMM Newton to pinpoint sources of X-ray contamination, in this case supermassive black holes, which had to be removed from the data in order to map the filament. In this image, you can see what they found. A filament of the cosmic web connecting 4 galaxy clusters, 2 on each end, each one as a white spot surrounded by color. The band of purple stretched between them, resembling a honeycomb or bone marrow-like texture, is the filament of X-ray emitting hot gas. Located in the Shapley supercluster, a supercluster of more than 8,000 galaxies, the filament stretches across a distance of 23 million light-years, which is the equivalent of about 230 Milky Ways end to end. Its mass comes in at roughly 10 times that of the entire Milky Way galaxy, and the temperature of the filament's hot gas is a scorching 10 million degrees Celsius. It reveals in detail for the first time how galaxy clusters are connected over colossal distances, and uncovers the vast cosmic web that underpins the structure of our entire universe, like the very bones of a cosmic skeleton upon which everything else forms. And according to the paper's co-author, the filament is exactly what we expected from the best large-scale cosmological simulations of the universe. We got it right. The latest breakthroughs in observing filaments lend important evidence and support for our current standard model of cosmic evolution, known as the Lambda cold dark matter model. The model is underpinned by dark matter, which has been too complicated for us to catch a glimpse of thus far, so observing this once thought missing visible matter on the cosmic web is a big step in the right direction. But to truly know whether our models match reality, we need more than 1 or 2 filaments. We need to map the entire skeleton, or at least much more of it. And that is where another mission, Euclid, comes in. Launched in 2023, ESA's Euclid mission is designed to piece together a more accurate picture of the cosmic web structure and history, and dig into the nature of dark matter and dark energy. Euclid will help us measure galactic shapes with precision, revealing how dark matter distorts space through gravitational lensing, and measure redshifts, giving us a 3D position for each galaxy. This combination will allow Euclid to infer the locations of the dark matter filaments, not just the galaxies on them, and give us precise locations to look for more gas. By 2030, Euclid will likely be able to confirm if the cosmic web matches results from the XMM Newton filament discovery, and the pattern seen in the cosmic microwave background. If it's a perfect match, that would be one of the strongest confirmations of the Big Bang model in the history of science. If not, then something is fundamentally missing in our standard model, whether it's our understanding of dark matter, gravity, or the early universe. Either way, with the help of Euclid and the latest observations of these cosmic filaments, cosmology is poised to be changed forever. One day, the universe, as we know it at least, is going to end. And nearly 30 years ago, scientists reached a general consensus on our universe's most likely fate. It is that over trillions of years, its galaxies will drift farther and farther apart. Stars will cool off and die out. Black holes will slowly evaporate, until all that's left is an infinite expanse of cold, dark space. This is the so-called Big Freeze. Powered by dark energy, it's a consequence of the accelerating expansion of our universe, by far the most likely outcome for the end of everything. Or so we thought. New, groundbreaking findings from the Dark Energy Spectroscopy Instrument, or DESI, may be uncovering a different story. It's found that dark energy's grip on our universe could be in fact weakening. But what does this mean? If true, and the cosmic engine that powers our universe is running out of steam, then the very fate of the universe hangs in the balance. I'm Alex McColgan, and you're watching Astrum. Join me as we investigate this profound shift in our understanding of the universe and explore why dark energy may be running out of power. Could it be that all our cosmological models are wrong? Or is there another explanation? Let's travel back to 1998. At that point, we already knew that the universe was expanding, thanks to Edwin Hubble's observations almost 70 years earlier. But scientists were still attempting to pin down exactly how fast. In fact, many were wondering if the expansion would eventually slow down. Logically, this seemed to make sense. The tug of gravity should bring everything closer and closer together over time, right? Now, all of this could be solved by working out the Hubble constant, a value that represents the speed at which the universe is expanding right now. It can be measured in two ways, by studying patterns in the cosmic microwave background, or by looking at distant redshifts. By the way, scientists have found that these two methods don't produce the same results, but I've got another video on that particular crisis that you can watch here to find out more. In this video, however, we're going to concentrate on the redshift method. Historically, the redshift of Cepheid variable stars has been used for this, but type 1a supernovae also work well. And without knowing it, the astronomers studying these immense explosions were on the brink of a jaw-dropping discovery. We know how bright type 1a supernovae should be, because they all explode in pretty much the same way: thermonuclear detonations of white dwarfs in binary systems. By comparing their true brightness to how dim they look from here on Earth, we can measure their distances. Then, by using the supernovae's redshift, the amount of light that has been stretched along its journey, we can determine how fast they're moving away from us, and therefore how fast the universe was expanding when their light was emitted. Easy enough, right? Well, when two independent teams of astronomers observed more than 50 type 1a supernovae, they found that the light appeared fainter than expected, which, although perhaps sounds trivial, turned out to be a pretty big deal. Teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that distant supernovae were dimmer because they were farther away than we expected. This was a huge revelation, as it came with a rather shocking consequence. It meant that the expansion of the universe was not slowing, but actually speeding up. Some unforeseen force was seemingly pushing entire galaxies apart. To visualize this, imagine if you took a marker pen and drew dots on the outside of an uninflated balloon. As you blow it up with air, the dots get farther and farther away from each other because the balloon itself, the space the dots reside in, is expanding in all directions. This unexpected result created more questions than it answered, a big one being, what is the force driving this acceleration? Unfortunately, the answer is still, we don't know. But it's been given the name dark energy, and most scientists think it's a property of the vacuum of space itself, the energy of empty space. Other scientists think it may be a type of energy fluid, or field that fills space, or even some kind of defect in the fabric of space-time like one-dimensional wrinkles, so-called cosmic strings. And others think it may just be a flaw in our understanding of general relativity on the scale of the observable universe, and that the matter could be resolved without the need for dark energy at all. But whatever it is or isn't, dark energy presents a mystery that is intertwined with the accelerating expansion of the universe. This was such a monumental discovery that, following the 1998 finding, Rees, Perlmutter, and Schmidt, the three astronomers who led the investigations, were awarded the Nobel Prize in Physics for their work. This discovery of dark energy gave rise to a new model of cosmology, the lambda-cold dark matter, or lambda CDM model. Lambda is a Greek letter that represents the cosmological constant. First postulated by Einstein, today it represents the mathematical parameters of dark energy. The other three letters, CDM, stand for cold dark matter. It's become what we today refer to as the standard model of cosmology, and it gives mathematical context to everything from the Big Bang to the future fate of our universe, and of course, all that happens in between. For decades, it's been the most widely accepted and most accurate model we have for the evolution of our cosmos. Confusingly, dark matter doesn't have anything to do with dark energy. We just use the word dark to describe two different things that we don't understand well. While dark energy is the force that's causing the universe to expand at an accelerating rate, dark matter is what we call the stuff in our universe that doesn't interact with the electromagnetic field. As in, it doesn't absorb or emit or interact at all with light. However, we believe it exists because we can observe its gravitational interaction within the universe, and the word cold in the model's name just refers to this dark matter having very little energy, since temperature can be thought of as a way to measure the energy of atoms. But if those two things make up the entire name of the model, the lambda cold dark matter model, what about everything we can see and do know about? It may not be reflected in the name, but it is captured within the model itself. Visible matter and radiation, including light, all belong to the category known as baryonic matter. Using independent measurements and observations, the scientific community has come to a consensus that under this standard model, about 68% of our universe is made up of dark energy, or this fundamental property of space-time that we know very little about, with visible matter making up only about 5% and dark matter accounting for 27% of our universe. Let that sink in. 68% of our universe is made up of something we don't understand and can't measure directly. However, a crucial aspect of our standard model is that lambda, or dark energy, is assumed to be a constant. Almost every cosmological calculation relies on this being fact. It tells us that our universe has an ever-accelerating rate of expansion, and that it will therefore face a cold, lonely fate. Galaxies will continue to drift further apart as the space between everything expands. Stars will burn out, die, and cool off. All of the heat and energy in our universe will be spread impossibly thin over incomprehensible distances until the universe's final temperature hovers somewhere barely above absolute zero, ending in what astronomers call the Big Freeze. But what if we're wrong? For the first time since the discovery of dark energy, we may have uncovered one of its key properties, and it's not what astronomers expected. In 2024, the Dark Energy Survey released the largest ever sample of supernova results from a single survey, having studied the deaths of more than 1,500 stars. Initially, the data seemed in line with the idea that dark energy is constant, but when they combined the data with other results, like measurements from the cosmic microwave background and earlier galaxy surveys, something didn't quite add up. It was starting to look like dark energy might, in fact, change over time. Now, a changing dark energy is not what scientists expected to find, and it caused them a big problem. Although it was a promising result, there were uncertainties involved, so it was nowhere near being decisive proof. To find out the truth, astronomers needed a far bigger, more detailed map of the universe to test whether this hint was real. And for that, they turned to DESI. Installed on the 4-meter Mail telescope in Arizona, the Dark Energy Spectroscopic Instrument is charting the optical spectra of tens of millions of galaxies and quasars across billions of years of cosmic history with one mission: to test whether or not dark energy is constant. Able to capture light from 5,000 galaxies simultaneously, DESI is measuring the position and receding velocity of some 40 million galaxies in order to accurately measure the expansion history of the universe over the past 11 billion years. This is a truly international effort, involving more than 900 researchers from more than 70 institutions around the world, and in 2025, the first major datasets were released. They included results from the first 3 years of the survey, with 2 more to go. And what they show is nothing short of extraordinary. DESI used data from nearly 15 million galaxies to build the largest 3-dimensional map of the universe ever created. This 3D map lets us fly through millions of galaxies, each containing 200 to 300 billion stars. Earth is at the center of this animation, and every dot is an entire galaxy. The blue represents farther galaxies from us, while the white shows closer objects. In other words, this map is almost unfathomably dense with galaxies. Using this data, a team of astronomers have measured baryon acoustic oscillations, or BAOs, from more than 14 million galaxies and quasars. BAOs are basically the fossilized echoes of sound waves from the early universe. By tracking how they change in size across cosmic time, researchers can work out exactly how fast the universe was expanding at any given moment. Here, the lighter blue color represents sound waves rippling through the primordial cosmic sea of our early universe. Over time, those slight variations froze in place, carrying with them a slightly more dense collection of matter. Over hundreds of millions of years, those waves would gather more and more material, eventually becoming stars and galaxies. These waves are still visible today in the form of the cosmic web. The researchers then combined this DESI data with other measurements, like the microwave radiation left over from the dawn of the universe, known as the cosmic microwave background, supernovae redshifts, and weak gravitational lensing, or how the light from distant galaxies warps due to gravity. And what they found added more weight to the 2024 discovery. Not only does it look like dark energy's influence is changing, but it's potentially decreasing over time. In fact, they found that dark energy's push may have weakened by roughly 10% in the last 4.5 billion years. You can think of it kind of like a foot still on the gas pedal but gently lifting, which means that the car is still accelerating but at a slower rate than before. Likewise, the expansion of our universe is still accelerating, but not quite as rapidly as it was a few billion years ago. And if dark energy is evolving, rather than remaining constant, then our standard model of cosmology is missing something, and something big. Assuming this model-shattering discovery is correct, it could mean a very different future for our cosmos. Instead of a big freeze where our universe expands forever, leaving us with a cold, dark, lonely end, we may end up experiencing an alternative reality. If dark energy's influence continues to weaken over time, decreasing until it becomes negative, then eventually expansion of our universe could stop altogether. Instead of a big freeze, it would end in a much more violent cataclysm. Imagine the raw power of the Big Bang, exploding and expanding out with enough energy, heat, and matter to form all the galaxies and stars across our universe. And now, imagine the exact opposite of that. A reverse Big Bang, where everything changes direction and rushes in toward a single point, with enough intensity to undo everything that ever existed in one cosmically colossal big crunch. I've spoken before about the possibility of a big crunch, as well as other theories about how physics gets weird at the end of the universe. If you want to know more, I recommend watching the video linked here. Now, if dark energy is an evolving variable, there is one other, perhaps even more important to us, impact. It means our current model of cosmology is incomplete. It could mean that the theory of general relativity needs modification too, and that there's more to learn about particle physics, possibly involving new fields or forces. But before we rewrite any textbooks, we have to be sure. And right now we're close, but we're not quite there. Sigma, or standard deviation, is the way scientists measure confidence. The higher the sigma, the less likely a result is due to random chance. And in the chase for evolving dark energy, those sigma levels have been climbing. On its own, DESI data lands us just above 2 sigma, which is about 95% confidence. Interesting, but nothing you'd bet your career on. Combine DESI with other instruments and the number rises past 3 sigma, even brushing the 4.2 sigma mark in some combinations. Roughly 99.997% confidence. While this is considered to be strong evidence, meaning that the result was unlikely due to random chance, it's still not quite at the level physicists require for it to be considered a solid discovery. For example, other evidence with this confidence level has turned out to be false before, so physicists typically wait for even clearer results before claiming a new discovery. The gold standard in physics comes when confidence reaches 99.99994%, which is sigma 5. And even then, things can still be wrong. For example, in 2011, physicists at the Gran Sasso laboratory in Italy measured some neutrinos arriving a few nanoseconds early, a feat that would require the particles to have traveled faster than the speed of light, breaking the cosmic speed limit. They reported a confidence level of 6 sigma, even more impressive than the gold standard for new discoveries. To put that into perspective, barring any unexpected mistakes in the experiment, 5 sigma represents about a 1 in 1.7 million chance of the result being a fluke, and 6 sigma is more like a 1 in 500 million chance of the result being wrong. So this was quite an astonishing observation, and it made headlines around the globe. Unfortunately, it was later revealed that the physics-breaking observation had actually been due to a faulty fiber optic cable and clock synchronization error rather than neutrinos breaking the laws of physics. Needless to say, there's still a little way to go with the concept of evolving dark energy. Now in its 4th year of the 5-year survey, DESI is well on its way to having measured 50 million galaxies and quasars, continuing to offer valuable data in the quest to understand dark energy. But it's not our only tool. Over the next few years, new experiments will be conducted. Other missions will further the exploration of the nature of dark energy, and complementary datasets will come out for analysis. The European Space Agency's Euclid and NASA's Nancy Grace Roman Space Telescope will extend measurements across even larger volumes of space and at higher redshifts. And the Vera C. Rubin Observatory will scan the sky for millions of supernovae, providing the enormous dataset needed to hopefully bring us to the 5 sigma mark. I personally can't wait to see what they find. But in the meantime, the new DESI findings are tantalizing and bring us to the precipice of a whole new view of both our standard model of cosmic evolution and the ultimate fate of our universe. Let me know in the comments what you think. Will the universe end in a big freeze? Or is a big crunch on its way? What ending or rebirth do you imagine for our universe? There's a crisis in the cosmos, and the fate of the entire universe depends on it. We've known that we live in an expanding universe since 1929, when Edwin Hubble first proved galaxies are moving farther and farther apart as time goes on. This expansion has come to underpin our entire theory of cosmic evolution, from the Big Bang to the formation of galaxies. The key factor is the rate of the expansion of the universe, a value that has become known as the Hubble constant. We thought this value was pretty set, But now, astronomers aren't so sure. Do we stand on the brink of a cosmic revolution? Or could it be that our entire model of the universe is wrong? I'm Alex McColgan and you're watching Astrum. Join me as we explore the crisis gripping cosmology, revealing how Hubble's greatest discovery has become one of today's most troublesome questions. For most of human history, the universe was small, or at least we thought it was. Some ancient civilizations imagined Earth to be flat and covered by a dome of stars. The sun and moon rose and set, and the constellations turned overhead. By the 2nd century, astronomers such as Claudius Ptolemy had envisioned a geocentric universe with Earth fixed at the center, and the sun, moon, planets and stars all revolving around us. This would be the reigning model for more than 1,000 years, until the 1500s, when Nicolaus Copernicus proposed a heliocentric model, where our Earth was one of several planets circling the sun, a revolutionary idea. Fast forward to the 18th century, and William Herschel mapped some of the stars in our galaxy, the Milky Way, proving that it was a vast, disc-shaped system. As antiquated as it may sound now, astronomers debated for some time whether the Milky Way was the entire universe, or if it was in fact one of several island galaxies in a much larger cosmos. That is until 1923, when Edwin Hubble resolved the question once and for all. Peering through the 100-inch Hooker telescope at the Mount Wilson Observatory in California, the world's largest telescope at the time, Hubble was able to resolve individual stars in Andromeda, and within them found his first Cepheid variable. Using Leavitt's law, named after Henrietta Leavitt, who found more than 2,400 variable stars and discovered that they could be used to measure distances across the universe, Hubble determined that Andromeda was some 900,000 light years from Earth, an astonishing distance. Too far away to be part of the Milky Way, this proved that another galaxy with its own stars existed outside of our own. Overnight, Hubble widened our view of the universe immeasurably. But he didn't stop there. He would go on to use Leavitt's law to identify 23 other galaxies and measure their distances, some as far away as 20 million light years from our planet. Ultimately, Hubble concluded that millions of other galaxies must exist outside of our own, forever changing astronomy. But Hubble's next revolutionary discovery also needed the work of Vesto Slipher, an astronomer born on a farm in Indiana in 1875. He joined the Lowell Observatory in Flagstaff, Arizona in 1901, and between 1912 and 1925, he made systematic observations of more than 40 spiral galaxies. At the time, it was known that the light observed from these distant galaxies could be split into spectral components, and depending on what elements were present in the light source, different patterns would appear. If the object being observed was moving away, then those same patterns would be present, only they would be shifted towards the red end of the spectrum, what we call redshift. Through years of observation, Slipher found that nearly all galaxies appeared to be moving away from us, but at the time, he didn't have a way to measure the distances to these faraway bodies, let alone their velocity. In 1927, Belgian scientist Georges Lemaitre proposed a theory that the universe was the same in all directions, and that if Einstein's theory of relativity was right, it must also be expanding. But he had no evidence to support this theory, so it was ignored for the most part. That is, until we bring Hubble back into the picture. Like most scientists at the time, Hubble was unaware of Lemaitre's theory, or of another similar one proposed a few years earlier by Soviet scientist Alexander Friedmann. Instead, from the observatory on Mount Wilson, Hubble made the same observation as Slipher, that galaxies seemed to be moving away from us. But he noticed something that nobody else had spotted before. The farther away a galaxy was, the more redshift it appeared to have, meaning the faster it was racing away from us. And this was happening in every direction. More observations revealed that almost all galaxies appeared to be moving away from each other, and that the redshift of a galaxy was directly proportional to the distance of the galaxy from Earth. This was a major breakthrough. It meant that the universe must be expanding. Hubble announced his finding in 1929, and following its publication, it became supporting evidence for Lemaitre's expanding universe theory, which would become known as the Big Bang. Hubble's initial measurement of the rate of the expansion of the universe, which would become known as the Hubble constant, was roughly 160 kilometers per second per million light years. That's about 500 kilometers per second per megaparsec. However, that number was not quite accurate, and even Hubble himself worked to refine it over his career. Since then, the Hubble constant has become a fundamental value in cosmology. We've used it to establish the age and the size of the universe, and those numbers are important for many, if not all, other cosmological calculations. To narrow in on the most precise value for the Hubble constant, astronomers have used two primary methods. But something about this value isn't adding up. One way astronomers measure the Hubble constant is through additional observations of redshift. In other words, the same way Hubble made his initial discoveries. Known as the cosmic distance ladder, or late universe method, it measures the expansion as we see it now, billions of years after the Big Bang. The more examples of distant redshift that we're able to get, the more accurate the measurement should become. Over the years, this has refined the Hubble constant to approximately 73.5 kilometers per second per megaparsec, quite a bit less than Hubble's original value. The other way to measure the Hubble constant is through the early universe method, a newer technique that estimates the expansion by rewinding the clock back to the start. This relies on images of the cosmic microwave background, or CMB, an ancient microwave radiation, which is, essentially, a snapshot of the universe from about 380,000 years after the Big Bang. This cosmic microwave remnant had been predicted in 1948 by Ralph Alpher and Robert Herman. Arno Penzias and Robert Wilson detected its presence in the 1960s, winning the Nobel Prize for their work. But it wasn't until later that we got a detailed enough image to predict the age of the universe with precision. In 2003, the Wilkinson Microwave Anisotropy Probe, or WMAP, released an all-sky map that showed the early universe, a time before there were even any stars. You can think of it like this. Imagine you come from the scene of an explosion that has already happened. You see fragments strewn all over the place, and you can't make out what the original object used to look like. But then someone hands you a snapshot of just after the explosion began. I bet now you could trace each piece back where it belonged in the original image. This is similar to how astronomers use the cosmic microwave radiation to trace our present universe back to just after the Big Bang. Most recently, in 2013, the European Space Agency's Planck cosmology probe was able to capture an even more detailed all-sky image of the background radiation, showing subtle fluctuations in temperature that would eventually ripple out to create dark matter webs, forming clusters of galaxies and voids across the universe. When astronomers take the image of the CMB and fast forward it to the present day, it's like pressing play on the video of the explosion. They get a predicted Hubble constant of about 67.4 kilometers per second per megaparsec. But you might notice this value is considerably smaller than the Hubble constant we've observed through redshift, which is a problem. I really can't stress enough how the expansion of the universe has become a pillar of our standard model of cosmology. The Hubble constant ties into our most fundamental physics, from Einstein's theory of general relativity to the idea that the universe evolved from a dense, hot, early state known as the Big Bang. Otherwise known as the lambda-cold dark matter model, it emerged in the late 1990s and has seemed to work beautifully ever since. An important feature of this model is that scientists expected gravity to slow the expansion over time, but instead, they've actually found it's now speeding up. Thankfully, this didn't break the model. Something seems to be pushing space apart faster and faster, and we believe that something is dark energy. As the universe grows, dark energy's effect becomes stronger, causing galaxies to move away faster and making the Hubble constant, the rate of our universe's expansion, increase over time. Both methods of calculating the Hubble constant are meant to give us the current rate of expansion, so it's not this acceleration that's making the results differ. But how can we have one unified cosmological model with two different values for such a fundamental rate? This discrepancy has become known as the Hubble tension, not because it represents an actual tension force, but instead, probably because of all the atmosphere it creates at cosmologists' dinner parties. And to be honest, I get it. It could mean we've got our entire cosmological model wrong. It was thought that as more accurate data was collected, these two values would converge on one agreed value Hubble constant. But therein lies the problem. As we've gotten more recent, independent measurements of the redshift, the number isn't converging. Instead, the gap is being reinforced. One independent measurement came from mega-maser hosting galaxies. These have certain molecules like water vapor that can amplify microwave radiation near a black hole at the center of a galaxy. This can create a maser, which is like a laser but with microwave radiation instead of visible light. Megamasers are extremely powerful, and their microwave emissions can be mapped precisely using telescopes. That means they can be used to measure the mass of the black hole and give a very accurate geometric distance to their host galaxy, allowing us to calculate the Hubble constant with, presumably, a very accurate distance measurement. In 2020, astronomer D.W. Pesce and others used this method to measure a Hubble constant of 73.9 kilometers per second per megaparsec, with 95 to 99% confidence. In other words, they were very sure. And in late 2024, another investigation by Daniel Skolnick, Adam G. Rees, and others resulted in a similarly shocking value. They used data from the Dark Energy Spectroscopic Instrument to study 12 different Type 1a supernovae that were dotted across the Coma Galaxy cluster around 320 million light-years away. What they found was a Hubble constant of 76.5 kilometers per second per megaparsec. Most recently, in 2025, researchers from the Inter-University Center for Astronomy and Astrophysics in India used mirror variable stars in our galaxy as anchors to measure the distance of mirror variables in faraway galaxies, a similar method to the original way of using Cepheid variables. They found a Hubble constant value of 73 kilometers per second per megaparsec. All of these measurements roughly agree, but fall far outside of the error range of the Planck measurements based on the CMB radiation. So something seems to be missing from our understanding of the universe. Astronomers, including two who worked on the DESI investigation, have been ringing the alarm bells. The paper's lead author, Skolnick, a professor of physics at Duke University, said, "Our model of cosmology might be broken," and noted that the Hubble tension is feeling more like a Hubble crisis. Without resolution, the model we use to interpret the universe rests on shaky grounds. Everything from when galaxies formed to how clusters evolve, and even predictions of the cosmic future hang in the balance. If the Hubble constant turns out to be the lower value calculated from background microwave radiation, then we live in a 13.8 billion year old universe that will likely go on expanding forever, a steady, predictable future with constant dark energy. But if the Hubble constant is the higher value observed from redshift, then our universe may be expanding faster than the current model predicts, and things may be weirder than we thought. If that were the case, then our universe may be younger, something like 12 to 13 billion years old. And it may mean that we're missing something fundamental in our understanding of the early universe, dark energy, or relativity. Some scientists have proposed that radical adjustments may be needed to reconcile the Hubble tension. These proposed adjustments have included things like decaying dark matter or dark energy that varies over time, and scientists have even explored the idea of modifying the dark energy equation of state, representing what could be a change to general relativity itself, something that may force us to reevaluate our entire understanding of not just the cosmos, but also our very understanding of physics. But another recent idea has been gaining traction, one that could save our model of cosmology without needing to rewrite physics. And all it needs to work is a little spin. No, really. The 2025 paper suggests that perhaps we've missed a very slow rotation or spin of the universe. Published by Balázs Endre Zigeti, István Zapudi, Imre Ferencz-Barna, and Gergely Gábor Banafoldi, the idea is that a very slow universal rotation once every 500 billion years would be slow enough to go undetected, but significant enough to affect how space has expanded over time. In fact, their preliminary calculations show that this slow spin could validate both values we have for the Hubble constant. When spin is introduced into the model, it predicts an early universe with a lower rate of expansion, like we get from the CMB calculations, and it also predicts a present universe with the higher rate of expansion, like we get from redshift measurements. These are exciting initial results. Zapudi, one of the idea's authors from the University of Hawaii, paraphrased the Greek philosopher Heraclitus of Ephesus when explaining the hypothesis, who said panta rei, meaning everything moves. And indeed, with how promising the initial results are, it may be true, entire universe and all. Though the authors were clear that this is just a preliminary calculation focused only on the Hubble constant. The next step towards solidifying this idea will be more complex models and simulations to check the hypothesis against other observations. I believe this idea is a reminder that there's still a lot to learn about our universe, but it's far too soon to think about throwing out our entire model of cosmic evolution, especially when we may be just on the brink of understanding the missing piece. And even if we can keep our cosmological model, it would still mean a new rotating variant of it, one where cosmic parameters and values shift to accommodate our new reality. And this idea has one other major perk. It doesn't violate any known laws of physics. Besides, I quite like the idea that not only is our planet spinning and our solar system rotating, but so too are the Milky Way galaxy and our entire universe.
If you've been following the Astrum Answer series recently, you'll notice that we've talked a lot about how the universe is structured. Filament structures of galaxies being pulled apart by the universe's expansion, with bubbles or voids forming in the gaps. Because of the universe's expansion, everything is moving away from everything. But of course, this isn't totally true in practice due to a mysterious force called gravity. Gravity is a pulling force, or technically, it is the curvature of space-time caused by uneven distribution of mass. On very small scales, gravity is hardly relevant at all, I don't feel any pull towards objects around me, only towards the Earth because it is so massive. Celestial objects close enough to the Sun are most influenced by its gravity, and all stars in the galaxy orbit around a supermassive black hole at the galaxy's core. But it doesn't stop there. You've probably heard that the Andromeda galaxy is hurtling towards us. How can that be when everything is moving apart? Gravity. Objects that are close enough together with a large enough mass are pulled towards each other by gravity faster than the universe can expand. This is why we have galaxy superclusters, and in fact we are part of one. Gravity is keeping these galaxy clusters bound together, meaning over extremely large timescales, collisions aren't totally unusual. In fact, a new theory has recently been proposed that the Milky Way may have recently experienced a collision with a large Magellanic Cloud-sized diffuse galaxy called Antlia II. Scientists have discovered that the Milky Way has ripples consistent with it having had a collision in the past, but we couldn't pinpoint what it collided with until Gaia discovered the Antlia II galaxy hidden behind our galactic disk. This makes it very hard to spot, as although it is massive, it is very spread out due to the collision, and being behind our galactic disk makes it hard to see due to the stars and dust in the way. But that brings us on to the main topic of this episode, the Great Attractor. In an opposite vein from the Supervoids video, where there are regions of space where there is an almost total absence of mass for hundreds of millions of light years in any direction, the Great Attractor is the biggest concentration of mass for hundreds of millions of light years. It is so massive that even though our galaxy is between 150 to 250 million light years away, we and all galaxies around it are currently moving towards it. Estimates put its mass at roughly 1,000 trillion suns, which is enough for many thousands of galaxies. But what could possibly be there that is that massive? Well, for the longest time, it was a total mystery, because, like Antlia II, the region where the Great Attractor is located is hidden behind our galaxy's disk. However, X-ray telescopes can see through the disk, and recent technological improvements and advances in X-ray telescopes have meant that we have been able to detect thousands of galaxies in the region where the Great Attractor is supposed to be. But the mass detected didn't add up. There wasn't enough present to create such a pull. Further analysis has revealed something very interesting, that while we are being pulled towards the Great Attractor, there is something even more massive behind it, located 650 million light years away, called the Shapley Attractor or the Shapley Supercluster. Located there are many thousands of galaxies densely packed together with a mass of 10,000 trillion suns, and everything within 1 billion light years is being pulled towards it. On the other hand, looking the opposite direction from the Shapley Supercluster, we see an underdense region, where everything seems to be moving away from it, called the dipole repeller. It isn't actually repelling mass, but due to all the mass around it being pulled towards more dense regions by gravity, it creates the illusion that it is repelling that mass. Although there are some scientists that do claim that an unknown repelling force is at work there. Simply put, we are still in very early days when it comes to understanding the universe. We do observe certain things, like the motion of galaxies, dense galaxy groups, and absences of galaxies in large voids or repelling regions. We observe the expansion of the universe and observe the filamentary structures. But the universe is an impossibly large place. We can only see so far, only live so long. Plus, our technology is limited. We have theories which try and explain what we see, but I really wouldn't be surprised to see these theories change as more data becomes accessible. Some may ask, what's the point then? However, I for one am hugely grateful for the bright minds working on this, as discovering our place in the universe is so fascinating. I'm glad humans have an insatiable need to explore and understand everything around them. This innate sense of wonder and curiosity is what drives the evolution of mankind, and I am excited to witness it.
A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape. A place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.